I'm Andrew Shentu.
I'm Mihir Gupta,
And I'm Isaac Harrington.
and we're Team 1040 from College of San Mateo in San Mateo, California. This presentation is going to be our presentation for our solutions for problem C of the 2024 SCUDEM competition. In problem C, we are told that humans hunted with a basic Clovis point spear. However, we weren't told exactly how they were used. We're given two conjectures. Humans either threw the spear at animals or they braced the spear against the ground and the animals would charge into the spear. We're going to try to answer the questions. Are spears more often thrown or braced? Which method is best for different animals? And what variables need to be changed to close the gap between the two methods? For the thrown spear, we know that the humans are farther away as they're throwing the spear towards the animal. However, there's less damage done to the animal because of that. For the braced spear, it's far riskier for the human as the animal is charging towards the human as they're holding the spear. However, it is much more lethal towards the animal due to the charging force. Some general assumptions that we had is that we're on flat land, our spears hit the same part of the animal every time, and that spear tip stays intact and attached every single moment. These are the general dimensions of our spear. For the throwing spear model, we have several assumptions. First, our constant throwing velocity is 15.27 meters per second. Our stationary target stands at 10 meters away from the human, and we're throwing at a height of 2 meters above the ground. Gravity is 9.8 meters per second squared, and air resistance scales linearly to velocity. Our goal for this model is to model the flight trajectory of a thrown spear at various different throwing angles, to maximize the velocity at a distance, and to find how the impact angle affects lethality. For the trajectory model, we modeled trajectory with an air resistance that scales linearly to velocity. Air resistance was modeled with parameter K, which went from 0 to 1. We picked 0.3 due to the spear being relatively aerodynamic, and we used differential equations to model the x and y accelerations, velocities, and positions of the spear throughout the air. We have the position graph here on the chart on the page. To model the spear inside the flesh, we have this diagram on screen. We have when the spear enters the flesh, it's slowing down due to drag from the flesh and until it hits the bone. We're assuming that upon impacting the bone, the spear imparts all its momentum onto the bone. If the bone requires a certain amount of force to break. If the bone breaks, the animal dies. If it doesn't, it survives. Another thing that we considered was how the angle of entry impacts lethality. We used differential equations to figure out how much more force we would require to break the bone at different angles of entry. To model the spear inside the flesh, we used drag formulas and assumed that the flesh behaves like a fluid. We found that the average density of flesh to be 1,000 kilograms per cubic meter, and we estimated the coefficient of drag to be 0.1 based off the chart on screen. We also found the cross-sectional area of the spear to be 7.566 centimeters cubed. We used differential equations to model the velocity and the position of the spear inside the flesh, and we found that the decrease in velocity due to the drag was very small, almost negligible.
When the spear contacts bone, it will have some velocity. By assuming the final velocity is zero, we can find the force it will exert on the bone using impulse. The change in momentum divided by the change in time would be mv over delta t. We had to assume delta t to be 10 milliseconds based on the impact durations of objects hitting brittle materials like ceramics. To find the force, we relied on the fact that we are applying stress on the bone, which depends on the area of the bone. If we treat the scalings of mass, size, and area using a cube, we find the force needed to break the bone is proportional to the mass raised to the power of 2 over 3. We use the bone strength and the mass of human as a baseline for our equation. To apply our models to different animals, we did some research on each animal's traits, which are mass, height, and speed. We are only able to find information about humans' bone strength. For the distance from skin to bone, we found anatomical images of various animals, estimated the thickness of flesh in front of the chest, and used Desmos to estimate a logarithmic curve connecting the points. This gave us the thickness of flesh for the rest of the animals. How will changing the mass affect lethality? Increasing the mass of the spear will lower the initial velocity of the spear. We represented lethality with momentum. Increasing the mass of the spear is more lethal, up until the spear misses its target. As a result, we can conclude that the closer you are to the animal, the more mass your spear should have to increase lethality. Here are the general results with the variables fixed to a 3 kilogram spear thrown at about 15.25 meters per second at an animal 10 meters away, with the time of impact at bone being 10 milliseconds. Almost all animals survived the spear, except for the deer and the wolf. One of the limitations is that we are only modeling one instance of damage. We assume the spear hits the chest, has to break through the bone to be lethal. However, a hunter will likely aim for weak spots like the eyes or neck. This model also loses accuracy since we kept the density of flesh constant, when in reality, the spear will travel differently through each animal. Lastly, we assume that the target animal doesn't move after contact. But for smaller animals, such as wolves, they will be impacted by the sudden transfer of momentum. So our model does not work well for smaller animals. Now, moving on to the brace spear model. We assume the animal would charge into the spear head on, and the spear is braced securely on the ground. The path of the spear in flesh is straight, and the initial entering angle is 30 degrees. We set the mass as the mass of the animal and the initial velocity as the animal's top speed. Our goal would be to apply the throwing spear model with modified parameters. With the 3 kilogram spear and the time of impact at bone of 10 milliseconds, we found that the brace spear method is 100% lethal. Our brace spear model has many of the same limitations as our throwing spear model. One thing to note is that this assumes all animals will run into the spear at their top speed, and this does not accurately predict animal behavior since some animals will flee rather than charge at the hunter.
As part of our investigation, we created graphs of the trajectories of the spears for a range of angles and determined which would hit our targeted section of the animal. For the woolly mammoth, we determined that from a distance of 10 meters away with our constant initial throwing energy, valid initial throwing angles to hit were between 12.6 and 17.7 degrees, represented in green on the trajectory graph plotted with MATLAB. Misses are in red. We found that any realistic throw would have the mammoth survive, and an extremely fast velocity of 454 meters per second would be required to kill it. For the brace model, almost any reasonable velocity of the animal when it impales itself on the spear would result in its death. The range of angles that was valid for hitting the grizzly bear was between 6.1 and 7.9 degrees for the same set of conditions as with the mammoth. Similarly to the mammoth, reasonable throwing speeds do not result in the death of the grizzly bear, and any velocity above 0.171 meters per second results in death upon contact with the brace spear. Lastly, we looked at the gray wolf. Here, a range of throwing angles from 4.8 to 5.9 degrees resulted in a hit on the gray wolf. Our initial throwing energy resulted in a lethal hit to the wolf at each of these angles, and similarly, the brace spear was lethal to the wolf as well. Much of our calculations and plotting for this project was done with MATLAB, and the following slides are a showcase of the code we wrote. At the top of our main file, we instantiate objects of the animal class with constructor arguments representing their mass, height, and charging velocity. Following this, we have the control section where we can set which animal we want to examine, the mass of our spear, the initial throwing energy, the collision duration when the spear hits bone, the distance from the animal, and also whether we want to utilize our brace model calculations or our throwing model. If the throwing spear is selected, a function is called to find each of the throwing angles that will result in a hit on the animal for the given parameters. For each of these valid angles, the lethality is then checked. The last code block here provides a plot of the mass versus momentum as we change the characteristics of the spear. Next, we have our function that allows us to determine the velocity of the spear in flesh at any point, taking advantage of the MATLAB differential equation solver. Following this, we have a function that determines the distance that the spear must travel through flesh based on the angle that it initially contacts the flesh with. The last function to determine lethality uses an impulse equation solved for force in order to compare the force of the collision to the bone strength of the animal and therefore determine if the hit meets our standards for lethality. This last MATLAB slide showcases our helper classes that contain functions to give us the velocity as the spear travels through the air, the angle at which it contacts the flesh, graphing of our trajectory graphs, and the definition of the animal class and its contained methods. In conclusion, our modeling found that throwing the Clovis point spear was almost always non-lethal for larger animals, at least for throwing velocities that could reasonably be achieved by humans. However, throwing spears were effective against smaller animals and safer for the hunter as well. Brace spears were always lethal for the animals that we tested with the assumption that they were always charging at the spear and always impaled themselves at a standardized spot on their body. Especially for larger animals, though, this posed a significant risk to the hunter of being trampled. The results of our modeling lead us to conclude that the same types of Clovis point spears were thrown and braced, with what technique was being used being determined by the size of the animal, the size of your hunting party, and the acceptable amount of risk of being trampled based on the animal's size. Here are our works cited pages, and thank you very much for listening to our presentation.